Hey everyone, welcome back. In this video, we're covering magnetism based on the FAA's Aviation Maintenance Technician General Handbook. Magnetism plays a role in almost every aircraft electrical system: generators, motors, relays, solenoids, and even magnetic compasses. If you understand magnetism, electricity starts to feel a lot less abstract. Let's walk through this in a practical manner. So, magnets, how do they work? Magnetism is defined as the property of an object to attract certain metallic substances. In general, these magnetic substances are called ferrous materials, meaning containing iron, or iron alloys such as soft iron, nickel, and alnico. Every magnet has two poles, a north pole and a south pole. Like poles repel each other, and unlike poles attract. The magnetic field flows from the North Pole to the South Pole in a continuous loop, and it's strongest where the field lines are closest together, right at the poles. Magnets always have two poles. You can break a magnet in half, but you'll never get a single pole. Each piece becomes its own north and south. Magnetism exists because of the alignment of tiny magnetic domains inside a material. When molecules line up in the same direction, the material becomes magnetized. There is no known insulator for magnetic flux or lines of force since they pass through all materials. However, they do pass through some materials more easily than others. Thus, it is possible to shield items, such as instruments, from the effects of flux by surrounding them with a material that offers an easier path for the lines of force. The lines of force take the easier path, the path of greater permeability, and are guided away from the instrument. Magnetism can be temporary or permanent. In the context of magnetism, soft and hard metals mean how easily do they magnetize and demagnetize. Soft metals, such as iron, are easily magnetized and demagnetized, which makes them useful in electrical equipment, while hard metals, like steel, hold magnetism longer and are used for permanent magnets. Mechanical shock and improper handling can weaken or destroy magnetism. This is important in aviation maintenance, where vibration and temperature extremes are normal. Now let's jump into electromagnetism. Electromagnetism is the direct relationship between electricity and magnetism. It was discovered in 1820 by the Danish physicist Hans Christian Ørsted. He found that when a compass was placed near a wire carrying current, the compass needle deflected. When the current stopped, the needle returned to normal. This proved something extremely important: electric current produces a magnetic field. That discovery led to the electromagnet and eventually to motors, generators, relays, and many modern electrical devices. The wire itself does not need to be magnetic. Ørsted used copper, which is non-magnetic. The moving electrons created the magnetic field, not the material. The magnetic field forms around the conductor in circular patterns. As long as a current flows, the magnetic field exists. When the current stops, the magnetic field collapses. The strength of this field depends on current. More current, larger magnetic field. Less current, smaller magnetic field. A compass can show the direction of the magnetic field. When current flows through the wire, the compass aligns itself perpendicular to the conductor, showing the field is circular. If the current direction is reversed, the magnetic field direction also reverses. We determine this using the left-hand rule. Imagine you grip the conductor with your left hand, thumb pointing in direction of electron flow, fingers curl in the direction of the magnetic field. If a wire is bent into a loop, the magnetic fields begin to combine. If the wire is wound into many loops, it becomes a coil. Inside the coil, the magnetic field becomes concentrated and acts like a bar magnet with a north and south pole. Placing a soft iron core inside the coil greatly strengthens the magnetic field. Because soft iron has high permeability, this combination, a current-carrying coil and an iron core, is called electromagnet. Two important things happen. Magnetic flux increases, flux becomes concentrated in this center. The polarity of the electromagnet depends on current direction. Reverse the current, reverse the poles. Magnetic strength increases when current increases, number of turns increases, better core material is used. Doubling the current roughly doubles field strength. Doubling coil turns also roughly doubles field strength. Thanks for watching. I hope this helped make electromagnetism clearer. If it did, please like the video and subscribe for more AMD ACS explanations.